on teaching brain anatomy with open source.
Thank you.
You're welcome.
So I'm Tara Lindsley, that's Wes Turner. Just to clarify that. So I am a professor and chair of neuroscience education at Albany Medical College. And some of you may remember that I came here last year to the Open Source Festival and talked about the development of a new learning resource for medical education that was designed to help students learn brain anatomy. And so about 5 years ago, a team of 3 faculty, 1 medical student, and an undergraduate from RPI got together to solve a challenge that I have been experiencing for the last 30 years, trying to teach medical students neuroanatomy. And what we came up with was based on the use of open source software, and it was a unique electronic library of human brain anatomy. And when I presented this last year, I met Luis Ibanez from Kitware, who turns out to be one of the original developers of the open source software that we found so useful. And we've been talking with each other, and I've been talking with Wes and others at Kitware for the past year. And the reason I'm back is to tell you, for those of you who don't know what I'm talking about, I will give a brief introduction about the software to bring you all up to speed. And then we're going to turn the podium over to Wes to talk about where we're going next. Because if you think about it, technology, 5 years of educational technology is a long time. And the way students were using their computers 5 years ago is completely different than the way students are using technology in the classroom today. And I will say there's hope because faculty are also evolving in the way they use technology. And so the tool has been so useful, we wanted to keep up with the technology. And we're educators, we're neuroanatomists, and Kitware has the kind of expertise that we need to keep up with the technology. So what I'm going to do is briefly So I'm going to briefly describe the software, again, for those of you who didn't hear me talk about it last year. And I'm going to also then do a very brief demonstration of the capabilities of the software, mainly because it illustrates just how powerful this open source software that the database is built on really is, and why it's so unique, especially for medical education. And then again, we'll go through how we might build a better virtual brain model, at which point I want you all to be thinking about how you might be able to contribute to the idea development and the engineering that it takes to bring the virtual brain software into the next iteration of medical education. And so we will talk about, just to get you thinking, about turning it into a compatible application for web browsers, for the kinds of operating systems that students are using on their tablets and smartphones. I mean, really, students don't carry backpacks with books in them anymore, heaven forbid. The idea that we could take unique models of human brain anatomy and using 3D printers generate solid models from the creative recesses of your brain to a handheld model, right, with 3D printing. And of course, as an educator, I want you to be also helping me, not just with the technology, but thinking about how can we better monitor how students are using these educational resources, how effective are they? You know, old school surveys of students, did you use it? Was it helpful? Looking at how they do on grades, it's just not the way we want to be able to track student use of these technologies. And so learning analytics, incorporating that into the way students are using this would be helpful. And of course, everybody loves games, and already, even in medical school, we are working on gamification where it makes sense from the learning objective. Gamification is a huge advance over what you and I all did with flashcards, right? It's effective, but it's mind-numbing. It's very boring. Anatomy in particular can be very boring to learn, and so gamification where it makes sense is useful. Hit that button. Okay. So neuroanatomy is important. I'm not going to try to convince you, except to tell you that for first-year students, we always tell them that all physicians must know brain anatomy, even if they aren't going to be neurologists. Otherwise, they glaze over and figure, I need to know the basics, but I don't really need to know neuroanatomy. It's simply not true. 45 million Americans visit their doctor where the chief presenting complaint each year, 45 million, the chief complaint is neurologic in nature, and only about 16% of those are referred to specialists like a neurologist, a neurosurgeon, for example. A lot of hospital admissions. The third leading cause of death is stroke, and so our students are going to be yours and my future physicians. They need to know brain anatomy, in particular because it's the foundation for diagnosing so many of these future patients that come with neurologic-related complaints. Next. Thank you very much, Russ. So, why is that such a big deal? Students dissect cadavers, they look at atlases, they look at models, like this one, right? We can say, well, this is my husband tells me I'm losing my mind all the time, but so we have models, solid models. What's so hard about learning the anatomy of the brain? Well, for one thing, a lot of the most important structures clinically can't be viewed on the surface. You have to look inside, okay? So why don't we dissect the brain? Well, for one thing, we don't have an unlimited source of human brains for dissection. But even if we did, and we could go back to grave robbing, which we won't, the human brain is translucent. With very few exceptions, the cells that make up the human brain don't have pigment. And so a lot of the structures are very small, they're very compact, and they look just like the neighboring structures. Even more importantly, clinical diagnosis often requires a spatial understanding of the relationship of these invisible internal structures. So for example, we have a patient that comes to the clinic and they have the following symptoms. This is going to sound a little illogical to you at first, and it does to our students. This is a person who is unable to move their right side of their body. They're paralyzed arm and leg on the right. They have lost touch sensation also on the right side of the body, but not on the face. They have no loss of pain and temperature sensation anywhere on the body. Yeah? That sounds illogical. How can we have such a weird array? Another patient might come in and they're suffering from infertility and double vision. Where is that? Students have to be able to know the anatomy and the function that goes with it so they can localize where the damage is occurring. It's a fundamental process in the diagnostic place. Next. So the brain is very complex. There are thousands of individual structures, all of them invisible. How have we been teaching students to learn neuroanatomy all this time? Well, we use traditional resources that pretty much look like this. And actually, could you go back, Bryce, just fine? By the way, that example I gave you of the patient with the illogical combination had a stroke that affected the territory that you see in that red triangle on the right side of the brain. This is the patient's left side. And that is a territory supplied by a particular blood vessel. And when that blood vessel is occluded, that combination of deficits is what results. And so you can multiply that by thousands. Thank you. You multiply that by thousands of different structures, all in combinations, supplied by various arteries that serve territories of the brain. So traditional resources also use serial sections that are staged to reveal the internal anatomy of the brain. You can see how you can really make out a lot of detail about the way the cells are arranged, the way the fiber tracts are connected. This is similarly stained. But what we've asked students to do over decades is to take serial sections of the brain from the forebrain all the way actually to the base of the spinal cord, hundreds of sections, and study them. And then do a mental exercise where they have to then picture how the structures that they visualized in 2 dimensions fit together in a 3-dimensional map. Right? So they understand who anatomic neighbors are at different points along the nervous system. It's a very hard thing for some students to do, and it takes a very long time. And again, it's like flashcards. It's mind-numbing to look at all these different sections. So this was the reason that we wanted to develop something that would allow our students to visualize the brain in 3D and in a way that didn't involve carrying around large, bulky models or wet, sticky brain specimens. Now, okay. So what would a resource like that look like? So we were imagining this in our minds, and we decided after talking to lots of students that we wanted it to be portable, flexible. We wanted it to be digital, and it had to be compatible with student computers at the time. At Albany Med, as in most medical schools around the country and universities, students are required to have a particular type of laptop. This was a laptop at the time. It's already changing to hybrid tablets, and we wanted it to be something where the students themselves, the user, could select the brain structures they wanted to visualize. They weren't stuck with a static model. We wanted them to be able to rotate the models in virtual space in 360 degrees. We wanted them to be able to zoom in and zoom out. And we wanted them to be able especially to see through surface structures to the deeper structures below them without making the surface invisible, because those spatial relationships are so important, right? So we wanted some ability to vary the opacity of the structures. And of course, for the faculty, we wanted it to have the structures that were most important for our first-year medical students to be able to visualize. So there were about 80 of them. We wanted also, because we're teaching medical doctors, we wanted them to be able to relate the solid structures that they could visualize on their computers to the MRI view that a doctor would see in a clinical setting. These are black and white grayscale images that you're all familiar with. And it had to be easy. Not so much because students aren't sophisticated enough to use it, but because the faculty aren't sophisticated enough to use it. Okay, so the next one. So we searched around, and it may surprise you that even 5 years ago, we could not find a virtual brain model that could do all those things. There were lots of animations online, but they were already chosen structures that would rotate in certain ways, and they were already structured, and not enough of them had all the important structures we wanted to see. Lots of big picture models, but nothing that really met all our criteria. So we found an open source software that was available thanks to the hard work of many individuals and organizations, some of whom are named here. This is a toolkit. It's a whole array of applications that were developed for the National Library of Medicine's Visible Human Project. And the one tool within this toolkit that we found most helpful was called ITK Snap. And this is an application that's designed to view medical images, like MRIs, in serial sections, to delineate and extract anatomical structures and render them in 3D. Now that sounded pretty good, and we looked at a couple of different things, but this was by far the most powerful and adaptable of the software that we were able to view.
That's okay, that's fine.
I'll reciprocate. All right, so how did we generate the structures? Well, this powerful software, ITK Snap, actually has an algorithm for automatically segmenting or colorizing the structures that stand out as different from neighboring structures. That is, they have a grayscale value that is sufficiently different from a neighboring structure that you can automatically separate it from its neighbors. But in fact, even with the high resolution MRI that we were able to get through collaboration with GE had a 3T magnet, which is a very powerful MRI machine. And we had a volunteer that was willing to put his head in there. We thought he was normal and healthy volunteer. I can say that because it was the medical student that did a lot of the work on the project with us. And so we got a very high quality MRI. And in fact, it's dense. And so standard MRIs have a lot of pixels, over 1 million. The MRIs that we were able to obtain with this machine had over 24 million pixels. And unfortunately for us, very few of the structures we wanted our students to be able to visualize could be automatically segmented. And so we had to hand color, using ITK Snap, manually segment all the pixels corresponding to all 79 structures that we wanted to visualize. It took about 9 months. And it took, and this is the reason I think that nothing like this had been done before that we were aware of at the time, is because not just anybody can segment the these structures. They're isodense, that is, they don't stand out from the neighboring structures. They're too small to be visualized or too gray to be visualized on the MRI. And so we used those atlases of serial sections and histology to make educated, hopefully well-educated, approximations of the location of all these structures. So they are not based on the real location of these structures. They are based on a histologist, neuroanatomist, a neurosurgeon, and lots and lots of trial and error. So we hand-colorized them and created what was a database of 79 structures. You can go to the next one. And this is what the software user interface looked like in the original ITK Snap with our segmented brain structures in color. These are 3 standard views of MRIs that you would see in a clinical setting. And that's all these 3, and this is the 3D window. Now, when we first released this software to our students, they loved it, but they kept screwing up the database because the free software that we used to visualize the database in 3D, which is the ITK Snap, had this little function called edit. And they kept hitting the edit button and changing things in ways that were irretrievable and having to go back and re-download things. So we spent the second summer fixing that. Go to the next one, by creating a simplified user interface. And this was really the work largely of the RPI student that worked with us as a summer research fellow. And what we did is you still have the 3 MRI screens and the 3D window, but we create, and you still have the color and opacity options that you had with ITK Snap. But now you have a structure list here. There's no edit function, but you have a structure list of pre-built models that are especially useful for our students to be able to visualize. And we didn't want them to have to build models that we knew everyone would want to build. So there's a list here including the basal ganglia, cerebellar structures, deep nuclei, etc. And we also have some groups and a structure list of the 79 structures they can visualize. There are 2 versions, a half brain and a whole brain. The vasculature, only major vessels are shown here, but it allows them to make their own or use the pre-built models. They can save them and retrieve them. They can share them on memory sticks or on a course management system. And we did create a few shortcuts. So when you're navigating around and building these models, one of the things that is difficult is recentering or starting all over again. And so we have a couple of hot buttons for show all, hide all, to recenter the axes. Students use this kind of thing by clicking on the structure and noting the name of the structure in the structure description window. And again, by building their models, they're actually handling, it's a lot like actually handling the material in a laboratory. And so it's a very effective educational tool. So the problem, as I mentioned, is that this is software. And even though it's 150 megabytes, it's very small, it's very easy to download. And you can get it for free, by the way, at the website that the slide showed before. However, people aren't using software much anymore. They want to be even more mobile than that. And they want to be able to access this kind of learning resource in other ways. And so this is just an example. I'm not going to do a demonstration of this because I want to give Wes a chance to talk about the future. But this is an example of the kind of custom model that you can make. You can look through the cortex to deeper structures that are called. I will let Wes do his thing.
So one of the things that we were really excited about when we had the opportunity to discuss this with Dr. Lindsley was the data was right with the application, the data was available, and the data was in a standard format. So right away we were able to read this into our own tool sets, we were able to start playing it. So as we got closer to this demo, to this time frame, we started looking at some of the new visualizations and the new paradigms we have put together. ParaView works with the visualization toolkit, ITK Snap works with is interfaced to that, and all of these lead us to this logical association of what can we do using our new toolkits, VTK, ParaView, which is a data viewer, it allows you to, it's largely used for scientific computation, CFD codes, etc. What can we do with her data that allows us to go in and show something new, shows the benefits of open data? Basically, I'm going to go past this, and we're going to start right here. What we found is that because the data is available, we can use readily available segmentation algorithms to go in and extract out the surfaces. Once we've done that, the same software that we use to display the results of scientific computations becomes available for use in displaying the brain models. So I'm going to go to the site. I hope it works. Okay, I'm going to quickly switch to another machine and go to that site. This is one of the benefits of open source software is we've been working together all morning, or last night, last couple of days, and in the end, we didn't quite get to the point of being completely agile development, thank you. Yeah, it wasn't the main function. Yes. So what we did, we managed to set up a website. We have software running on a server on Luis's laptop. Hopefully it's still running. There we go. And okay, what we did was we segmented out a bunch of the, I think it's like four amygdala, caudate, glutamine, and fornix. We just segmented out 4 structures. There's conceptually no reason why we couldn't do all 80. In fact, we started on that, but our tools were taking too long and we ran out of time. Like I said, this has been an agile development exercise. This is running on his laptop. We're able to display it here. And we can actually go through, if I can see it, we can actually go through and do the same 360 type of visualizations for turn on and off.
Where's the mouse?
It should be refreshing right now. That this is one of the hazards of a live demo. We're running some bandwidth issues, or some of maybe Luis's machine, a little tied up right now. Sorry? Yeah. So in any event, what we're able to do is this is being served on his machine. We can bring it up, we can view it in the browser, and as soon as we get this up and actually rendering again, if you guys go to the same website, and I'll go back to that slide so you can see that. So you can see the code. Once we get this back up and moving again, what you'll find out is that you can actually interact with the code. You can set up a server. Now, as part of this, and I'm going to come back to that if we have an opportunity, but as part of this, one of the other things that we're able to do is Luis has actually put this code out there on the web. Let's put this code out there on the web. If you go to this GitHub account, SUNY Albany Brain Anatomy Explorer, you can actually download the entire code base, including the segmentation software that will allow you to generate new surface models from Tera's data. You can also go in, and we have this mirrored at Luis Vanya's GitHub account. Actually, I think this one's more complete right now, but I'm going to make sure that Luis updates the other one as soon as we're done with this meeting. But the idea is you can go in here, the code's available open source, we have Terrace data is available, we have the code to do the segmentations, you can put your own segmentations into a simple data directory. Once they're there, they become available for use. And all of this has been enabled by the fact that we have a nice set of segmentations that took a long time to put together. And by making that available publicly, we can go in and add some other software flavors to it that allow us to actually go through and sure, you take a USB MHD.
It's technology.
Okay. The other cool thing about this is we've been able to do this for a number of different programs. So we've actually taken this code, we've loaded it into something we did for Dartmouth. Dartmouth has an application for doing analysis of optical flows through tissue so that they can look for cancers. It's called NearView, NearFast software. If you look at Dartmouth, search for NearFast, you'll find our code as a NearView viewer. You can go in there and you can hand segment these as well, or segment these based on their label values. They're labeled from 0 to 79, so there's a key that goes along with it. You can tell which piece of anatomy is which, and you can go through and apply that as well. So, again, once we solve the network problems, this will actually be up on your machines. It's been working most of the day. It's now actually showing on my machine again, and I apologize for it.
You will see it also in a cell phone or a tablet.
It actually works a lot better on a cell phone because it's a smaller picture. All right, I guess that's what I'm